Now that we have the basic idea of what hypothesis tests are all about, let's take a look at conducting a hypothesis test for the mean. Now consider this data, which consists of the time it took 15 students to complete an in-class quiz. Is there evidence to suggest the typical time it takes to complete the quiz is greater than 10 minutes? Now this word typical, to me right away, I know I'm talking about the mean or the median. Now, and I also want to look at this data. This data tells me right away that I'm also talking about the mean and the median, or the median, because this data, you could argue, is either ratio or interval. Now, it's time to complete a task, so it's like ready, set, go. There is a natural zero, so the interval won't work. This is definitely ratio data. So again, the ratio data points to the idea of the mean or the median. The idea of a proportion just would not make any sense here. Now, we're going to actually use this data to complete examples of hypothesis testing for both the mean and the median. In reality, only one would be correct, but we'll walk through the process and use the same data for both. Now, before we actually start it, I want to walk through what I think are some basic steps for completing a hypothesis test. Now, the steps 1 through 7 are not formalized anyway. If you were to ask me in class, what about step 5? I wouldn't know what step 5 is. It's not like I have these memorized. To me, this is just simply a natural, logical progression that you should always go through. Whether you call it step 1 through 7 or no steps at all, just do all of these. That's totally up to you. Now, the first thing you should always do is identify the parameter. We just did when I said this is obviously either the mean or the median. We want to be able to state the null and the alternative hypothesis, and then identify the appropriate test statistic. Now remember, we talked earlier about the difference between Z and T, and that will apply here. We want to state the assumptions and how you know that they're reasonably satisfied. How did you satisfy them? You can't just simply state what's needed. You have to tie in what's needed with your scenario to show that the assumptions are reasonably satisfied. Then we're going to calculate the p-value. Then based on the p-value, we will state our decision. The decision means simply, are you going to reject the null hypothesis, or are you going to fail to reject? That's your decision. Then you're going to state your conclusion in English. In other words, there is enough evidence to suggest whatever it is you're trying to show, or there's not enough evidence. That's what this is all about. Is there enough evidence to state or to show what you're trying to show? So let's go ahead and complete the hypothesis test for that quiz data. First of all, step 1, I want to state the parameter. The parameter is mu. We're interested in the mean. Now, in reality, when we walk through this, you're going to see here in a moment that we may have to switch this. If the assumptions aren't satisfied for the mean, then you should switch it to the median. Now, this next step, we need to state the null alternative hypothesis. So I need to go back up here and see what they're asking. Is there evidence to show the typical time for the quiz is greater than 10 minutes? So that tells me the null hypothesis, H naught, will be that mu is equal to 10, and the alternative hypothesis is that mu is greater than 10. Now also, we need to state the significance level. So I'm going to slip that in here. Alpha, it didn't say in the problem, so as a general rule of thumb, we use 0.5. Now the test statistic that we want to use is a t. We want to use a t-test. We can't use a z-test because if you take a look at the assumptions, it's the same set of assumptions that we looked at before, or guidelines when we talked about confidence intervals. Do you know sigma? And the answer is no. So that tells you to look at a t-distribution. If we knew sigma, then we would be considering a z. Now we need to address the assumptions. The assumptions is that the population is distributed normally. So to address this, we'll take a look at a normal plot of the data. So here on TC Stats, I will select the normal plot and then the quiz times. And look at this data, you can see there's no doubt this is not normal. There's gross violations. All this down here, this is a huge problem. All this up here, there's just no way. So then what you need to do is draw a rough representation of what you saw in the normal plot. It doesn't have to be perfect, but it's got to be good enough so that when I look at it, I can say, yeah, they actually did the normal plot and they actually looked at it. So this is not normal. Now, this is very important. At this point, we should switch, and we normally would switch to the median. Okay, so we'd switch to the median and do a hypothesis test for the median, which is based on the binomial. For this example, we're not going to. I'm going to keep going and showing you how to do it for the mean, as if it was normal. Then we'll come back and do it for the median. So for right now, we're going to pretend like this was normal. But at this point, it's important for you to understand that looking at this data, the proper thing to do would be to switch to the median and continue, which I will show you next. But for right now, we'll continue with this as if it was normal. So the next thing we need to do is find the p-value. So if I go back to TC Stats, I'm going to go way back and select one sample, and then there's a t. Now this is the null and alternative hypothesis that we stated earlier. The null hypothesis we set to equal, and it was 10. And the alternative hypothesis was greater than 10. Now the confidence level is not needed here. You put it in if you're actually calculate a confidence interval. It's not needed here, so I'm not going to bother with it. I will tell it to select the variable, so it's going to use the variable quiz times. If I didn't have the data, I could easily simply enter the mean, standard deviation, and sample size. Now if I tap update, this is the value of t, and this is the p-value. So my p-value was 0.0098, and the value of t was 2.6351. Now, based on this p-value, the p-value is less than alpha. And remember, alpha is a probability of a type 1 error. So the p-value is saying essentially that the probability of committing a type 1 error is smaller than what you would allow for. We would have allowed for 5%. Therefore, it's safe to reject. So you would then reject the null hypothesis. And then you would state there is enough evidence to suggest the typical time is greater than 10 minutes. Now, I want to go back to this value of t and this p-value, and I want to talk a little bit about what just happened. The t-test statistic looks like this. T is equal to x bar minus the mean under the null hypothesis divided by the standard deviation over the square root of n. See, this is very much like a z-score. Remember, a z-score looked like the observed value minus the mean divided by the standard deviation. Well, the observed value here is a sample mean. The mean, mu, in this case, is what we stated it was under the null hypothesis. So x bar here was 11.7 minus the mean under the null hypothesis, we're testing to see if it's greater than 10, divided by the standard deviation, which the sample standard deviation was 2.4986, which is then in turn divided by the square root of 15. Now, we think of this just like a z-score, because essentially it is. It's just, rather than sigma, we're using s. So this value turned out to be, as we said, 2.6351. That means essentially the t-distribution is centered at 0. So up here is my sample mean, 11.7. Whoops. The t-distribution is centered at 0, but that's what this does. This is 10. This is the mean under the null hypothesis. This is what we're thinking that mu is actually equal to. And then this converts this to like a standard normal. That's what a z does. This converts this to a t. In which case, when it converts it, the distribution will look like this. 0, and up here is 2.6351. And what's happening is the area under the tail, this right tail, above 11.7 is equivalent to the area above 2.6351 was converted to a t, similar to converting it to a standard normal. And this area here, this probability, is 0.0098, which is exactly the same thing this is, 0.0098. And this is what we refer to as the p-value. So a p-value is actually the probability of observing a test statistic at least as extreme as we did see it. That's the tail probability. This is very, very similar to what we did with the normal distribution. It's the exact same thing that we did, except for it's a t-distribution because we don't know sigma. We have the standard sample standard deviation instead. But the concept is exactly identical. So in a sense, we can say that this 11.7, the sample average that was observed, is approximately 2.6 standard deviations above the mean. And we know that anything above 2 standard deviations is very unusual. So all this stuff in here that I just did is what TC Stats does for you in the background. This is how it calculates that test statistic. And we can think of that test statistic very much as being the number of standard deviations above the mean, where the standard deviation is now s divided by the square root of n. So this decision up here to reject and this conclusion, what this is really saying is that the sample average of 11.7, the difference between 11.7 and 10 is most likely real, not simply a matter of chance. As I did earlier when I first started talking about this concept, this is really saying this 11.7 does not belong to this distribution with 10 as a mean. It belongs to some other distribution up here, which has a greater mean, somewhere near, most likely somewhere near 11.7. This value belongs to this distribution. It does not belong to this distribution. Okay, in the next video we'll take a look at going through the exact same process, only it'd be for the median.